So let's look at the current valued Hamiltonian. Now maximize this functional between 0 and capital T, capital F x of t, y of t times e to the power negative rho t dt, subject to x dot equal to g of xt and yt, and x of 0 is equal to x naught. The regular Hamiltonian for this problem is h is equal to f of xy e to the power negative rho t plus lambda g of xy. Now notice that the integrand f is multiplied by e to the power minus rho t, which means we are discounting it. Remember, whenever we multiply something by e to the power minus rho t, we are effectively dividing it by e to the power plus rho t, which is a discounting exercise, right? So we're discounting it. We define the current valued Hamiltonian as h sub c, which is equal to h e to the power rho t. It's just a regular Hamiltonian h multiplied by e to the power plus rho t. Right, so this time we are not discounting it, but compounding it. However, this expression implies that h is equal to h sub c e to the power negative rho t, which means that the regular Hamiltonian is a present valued Hamiltonian. Right, so the regular Hamiltonian, since it is multiplied, since it is the current valued Hamiltonian discounted, it makes it a present valued Hamiltonian. Recall mu is equal to lambda e to the power rho t. Mu is a current valued co-state variable, and lambda is equal to mu e to the power negative rho t, which means lambda is a present valued co-state variable. Hoy makes this distinction between present valued and current valued. So whenever something is discounted, he calls it a present valued variable, and if something is compounded, he calls it a current valued variable. Right, so you need to understand this distinction. The first order conditions for the current valued Hamiltonian are as follows. So this is the current valued Hamiltonian with a new co-state variable mu. The first order conditions, del hc by del y is equal to 0. So this is just like the first order condition of a regular Hamiltonian. But now we have a different pair of differential equations for the co-state and state variables. The differential equation for the state variable is the same, right? X dot is equal to g of xt yt, which we get from here. X dot is equal to g of xt yt. So that remains, but we have a new differential equation for the new co-state variable, and that is mu dot minus rho mu is equal to minus del hc by del x. And these two equations need to be solved, possibly simultaneously. Our boundary conditions are x of 0 is equal to x naught, and mu of t, capital T, e to the power negative rho capital T is equal to 0. So this is the new transversality condition. Now, a few things to note. When t is finite, mu of t, capital T, is equal to 0. So if t is finite, then e to the power minus rho t or minus rho t becomes a large number. So e to the power minus rho t, which is 1 by e to the power plus rho t, right, means that you're dividing mu of t with a large number, and that is approximately equal to 0. So when t is finite, mu of capital T is equal to 0. The differential equation for mu is derived as follows. So recall that lambda dot is equal to minus del h by del x from the regular Hamiltonian, but minus del h by del x itself is equal to minus del hc by del x e to the power minus rho t. Now lambda, remember, is equal to mu e to the power minus rho t, right? This is our lambda. Lambda is mu e to the power minus rho t. Excuse me. So lambda dot is equal to minus rho mu e to the power minus rho t plus mu dot e to the power minus rho t, which is, so we're using the product rule to totally differentiate the right-hand side of this expression. And we can substitute, since lambda dot is minus del h by del x, and minus del h by del x is equal to minus del hc by del x e to the power minus rho t, this expression for lambda dot is equal to minus del hc by del x times e to the power minus rho t. So mu dot minus rho mu is equal to minus del HC by del X. Okay, when you cancel out e to the power minus rho t on the left-hand side and the right-hand side, right? Then you get this final expression, which is the differential equation governing the new co-state variable. So let's look at an example of a current valued problem. You want to maximize between the lower limit of 0 and the upper limit of capital T, e to the power minus rho t, it's a current valued problem, times ax minus bx squared minus cy squared dt subject to x dot is equal to y minus alpha x and x of 0 is equal to x naught. Set up the current valued Hamiltonian. So you have hc is equal to ax minus bx squared minus cy squared plus mu y minus alpha x. So mu is your new co-state variable. The first order conditions, del hc by del y, which is equal to minus 2cy plus mu is equal to 0. You set it equal to 0, which gives us y is equal to mu by 2c. Then you have mu dot minus rho mu is equal to minus del hc by del x. So when we differentiate hc with respect to x, partially differentiate hc with respect to x, we get minus a minus 2bx minus alpha mu, which implies that mu dot is equal to alpha plus rho mu plus 2bx minus a. Furthermore, we have x dot is equal to y minus alpha x, right? But y is equal to mu by 2c, so we have mu by 2c minus alpha x. Thus, we end up with two equations. Mu dot is equal to two differential equations. Mu dot is equal to alpha plus rho times mu plus 2bx minus a, and x dot is equal to mu by 2c minus alpha x. This pair of differential equations needs to be solved simultaneously. And using the appropriate techniques, which are to be found in chapter 24 of Hoy, we obtain the following solutions. Mu of t is equal to c1 e to the power r1t plus c2 e to the power r2t plus mu bar. X of t is equal to r1 minus rho minus alpha by 2b times c1 e to the power r1t plus r2 minus rho minus alpha by 2b times c2 e to the power r2t plus x bar. And the values of r1, r2, mu bar, and x bar are obtained from the differential equations, these differential equations, right? You can work with their homogeneous form and solve them simultaneously, but they will give you the values of r1, r2, mu bar, and x bar. The value of t is not given, making this a free endpoint problem. So whenever t is not given, you are free to choose it optimally, and then you can make use of the transversality condition. So utilizing the boundary conditions, x of 0 is equal to x naught, and mu of t is equal to 0, because t is finite, we have mu of t is equal to 0, we can solve for c1 and c2. So we end by looking at an economic interpretation of lambda and the Hamiltonian. Lambda of t is the shadow price of the state variable x of t. Lambda of 0 is the amount by which j star, the maximum value of j, remember j is our functional, by how much would j star increase if x of 0, which is the initial value of the state variable, were to increase by a small amount. That value is given by lambda 0, is captured by lambda of 0. Mu of t has the same interpretation as lambda of t, but it is for a current valued Hamiltonian problem.